Welcome! In this series of short videos, we will look at topics for both the PowerBasic Windows and console compilers. Today we will look at the topic of isometric graphics on a graphics control or window. Isometric graphics have been quite popular in many games for a long time. The three images we have in our folder here are all isometric graphics. They are basically a two-dimensional representation of a three-dimensional object. Our first graphic here is in the PNG format. As you will see from the other two graphic files in here, these are both bitmaps. The coloured area of this graphic is what we wish to show on the screen. The area of the graphic which is currently coloured black will be transparent for the user. And our last graphic is a mask of the previous one. We will use these two graphics together to display our graphic on the map, which will allow us to overlap these graphics so that the transparent area is not shown to the user. We have shown this technique before in some previous videos, but we're going to revisit it today. The code we're going to be looking at is in the PowerBasic Windows compiler. However, the same code can just as easily be used in the console compiler. Although the console compiler does not have normal windows, it does have a graphic window, which can be used in the same way as a graphics control on a window in the Windows compiler. Let's have a look at our code. This is the code for our Windows dialog. This dialog has very little on it. We're defining the dialog using the dialog new pixels command. If the word pixels is not used, the dialog is created using dialog units. Today we'll be using dialog new pixels so that we can control everything right down to individual pixels. The only control on this form is a graphics control. The graphics control is what we're going to use to draw all our graphics on. In our callback function, the event handler, this is where we're going to put a lot of our code. Firstly, we want to attach our graphic control so that any writing we do to the graphic object will be written to that control. We can perform that quite easily by using the graphic attach command. This takes a number of parameters. The first parameter is the handle of the dialog itself. We can obtain that using the cb.handle. The second parameter is the handle of the graphics control we wish to attach. And the next parameter, which is optional, is the redraw command. Using the redraw command means that any commands we issue to write to the graphics window will not be displayed to the user until such times as we execute a graphic redraw command. This vastly speeds up the drawing of images to the graphics control. The next thing we'll do is we will clear the content of the graphics control and we will make the background colour black. If we run our application now, we will see our form is displayed on screen and the graphics control is shown in black. This shows us the extent of the graphics control. Next, we're going to create a function to populate this graphics control with our mapping details. So we're going to call a new function called buildGraphicsMap, which will take only two parameters. The first being the handle of the form, and the second being the handle of the graphics control. We're following that with a graphic redraw command to tell PowerBasic to redraw all the pending graphics writing operations to the screen. So let's start to create our buildGraphicsMap function. In our function, we will be referring to two bitmap files, the mask and the map. We're going to load both of these into our application and then display them on the screen. So I'm going to create two local variables to hold the path and the name of each of these files. And we'll populate these variables by putting in the exe path, which is the path to where our executable currently sits, and our bitmaps are held in a subfolder called graphics. So this will load the name and path to each file into these variables. Next, I need to determine how big these files actually are. We can do that quite easily by opening the file for binary. Opening the file for binary and using a get command to pull back the width and the height of our bitmap. This we will store in the width and the height variables. Since both bitmaps are exactly the same size, we don't need to open the other file. Next, we will want to load these bitmaps into memory. So first we'll declare a couple of variables we can use as handles to these areas of memory. We'll call these handles BMP and BMP mask. PowerBasic supports this by the graphics bitmap load command. This command takes a number of parameters, the first being the name and path to the file, next the width and the height, and finally the handle to pass back to. So this will load both of the bitmaps into memory and return the handles. We're now ready to start displaying these on the screen. In order to do that, we'll need to know where in the screen we want to start drawing. So we will set up an X and a Y coordinate to start us off. And we will populate both of these variables with some values to place it roughly at the top and the middle of the screen. For a graphics window or a graphics control, the coordinates start at the top left-hand corner of the control or screen. Those coordinates being 0, 0. As we want to display a series of rows and columns, we'll need to have a height and a width offset for each subsequent row and column. So we'll set those values based on the size of our current bitmaps. So I'll create another two variables to hold these offsets, and we will populate those values now. There are a number of ways of working out where on the screen we want our bitmap to go. But one easy way of doing it is to use an array to store the coordinates of each of the bitmaps. This way you can work out the coordinates ahead of the game and then run through a for next loop to display them on screen. Since we're going to be holding these coordinates in an array, we'll need to know how big the array is going to be. We'll start off with an array of 5 by 5. So I'm going to be dimensioning a 3-dimensional array. An X, Y and a Z. So I'm using the X and Y to work out our position on the grid. And the Z coordinate is going to have two elements. This to hold the X and Y starting positions in pixels. So we're going to do a nested for next loop, working out our column and row positions. And within this for next loop, I want to work out what the X and Y coordinates to start are. So this will be working out the X coordinate. And since we have set the starting position to be 280, I want this to be the starting position plus the width of our graphic. So each time the routine runs through this for next loop, the size of the X coordinate will get bigger. And for the Y coordinate, it's going to be the current Y coordinate minus the height offset divided by 2. And having stored those values, we're now going to add the offsets. This will allow the X and Y starts to be amended before the next row is calculated. And after we've done each row, we'll want to update the X and Y starting again. This means when we get to the end of one column, we can then move up right to the start of the screen again. So we're using the stored value that's in the first element of each column. I know this may sound fairly complex, but it's a piece of arithmetic to basically work out where we next have to position our bitmap on the screen. Now that we've worked out all the coordinates, we can actually start to print out our bitmaps. And this is going to be by another for next loop. And now we get to the point where we're going to position our bitmap on the screen. This is a two-stage process. We're first going to copy onto the screen our mask. We'll be doing this using the graphic copy command. The graphics copy command takes a number of parameters. The first is the handle to our bitmap mask. This is the one we created earlier with the load bitmap command. Our next parameter is the handle to the graphic window itself. And then we have to deliver two coordinates, the x and the y coordinates. These are the ones we calculated in the routine above. And the final parameter is a parameter that tells it how to handle the bitmap. In this case, we're using the mixed mask source command. Having put our bitmap mask on the screen, our next task is to copy the bitmap itself. This is using exactly the same command, but with one slight difference. We're doing graphic copy on the bitmap handle, and the final parameter is mixed merge source. The combination of these two graphics copy command will place our graphic on the map, and any area on the bitmap which is black will not be displayed, thereby allowing the underlying graphics to actually be visible. Our final command in this routine is graphic bitmap end, to free up the area in memory we've actually used for our graphics. Now if we compile our application to make sure we haven't missed anything, it compiles cleanly. So if we try running our application now, let's see what it does. Well, it has displayed on screen our graphic a number of times. We have both 5 rows and 5 columns. As we're starting from the top of the screen and working down, you'll see that the graphic has displayed correctly. The hexagonal shape is concealing the graphic behind it. We can amend our map by making it a little larger. We can do that by amending these two values. These are the maximum values of x and y. If we make that 7 by 8 and then run again, we will see that our graphic has actually grown in size. And it does show deceptively as a 3D map. All our graphics are sitting at the same virtual height. We can get more of a 3D effect by amending the virtual height of one or more of the graphics. Since we have stored all the graphics in an array, all we need to do now is to adjust the heights. So in our code, in the area between when we determined the coordinates and when we displayed the graphics, we will put a little for next loop in here to adjust the heights. This is stepping through from row 4 to row 5 and row column 4 to 5. We're amending the value of the y coordinate by adding on 40 pixels. Since the coordinates go from the top of the screen down, this means there will be 4 of our graphics which will appear lower in screen than the ones surrounding them. If we try running that now, we will see that 4 of the cubes appear now to be lower than the others. And it's giving a very good illusion of being three-dimensional, all without us having to use any hidden line removal. If we want to make one of the cubes higher than the rest, we can reduce its y coordinate. If we decide that the cube at coordinates 3 by 3 needs to be raised, we merely have to reduce its y coordinate. This will move it further to the top of the screen. So if we subtract 20 from the y coordinate, and if we try running that now, we'll see that 3 by 3 is now higher on the screen. So this gives you a very easy way of displaying something in a three-dimensional form on a two-dimensional screen. And so far we have only used one bitmap. You could quite happily use a number of different coloured bitmaps to get a different effect. For example, a three-dimensional chessboard. However, we'll leave that for a different video. That's it for today. Thank you for watching.